Hi, I hope you're having a good day. Today we're going to talk about advanced SQL. And it just sort of picks up where we left off in Chapter 7. Talks about some other features, more about joins and things. And so, away we go. Well, we're going to be looking at more detailed join syntax and thinking about that. We'll also see how the functions are used in different types of there's lots of different functions that do strings and conversions. There are lots of date things in databases, and I guess it makes sense. What we're storing here is historical data. And then we'll also see that you can use set operators in SQL statements too, and I've found them very useful. I've used unions numbers of times. And then finally we'll see about this idea of writing programs and procedures in SQL, and that I think will take the final step for you. And finally we'll talk a little bit about embedded SQL. Well, the join operator is what we use. I usually use inner joins in my SQL. You'll see some of it when we do the online survey system database. And so what you're looking for is the equality of your primary key and your foreign key, or the inequality of it. An inner join is the one we deal with almost 90% of the time, probably, and that's where the values of the primary key match the values of the foreign key. Occasionally we'll do an outer join where we want to find, in addition, one or the other, whether we want to find all of the instances from the first entity, whether they have a match or not, or vice versa, find all the rows in the second table, whether there's a match in the first table or not. Well, I never have used a cross join. I guess it's really just a Cartesian product, returns all combinations of rows from the two tables. This is not a very common activity. Well, the inner join, where you have you list your tables, they call it the old style, right? And then you show your value, your attribute C1 in T1 equals the value T2 in C2. And so that's a join. Now, we've also moved to this type of syntax where you do a join on, where you specify the variables. Usually natural joins, and you can see here's the clause that says the same thing. The C1 in table 1 and the C1 in table 2 are going to be equal. And I just think that's why you should do it if you're going to use a join. And I use the inner join in a lot of my syntax in my online survey system. So these other forms are cute, but in real life, you're not going to use them because you're never going to have two attributes that have the same name if you're following a decent naming convention. So they're sort of just, yeah, you could do it, but you won't. The outer join is the idea that you get all the rows from one table, whether they have a match or not. Remember, on an inner join, the only rows returned on the result set are those rows where the values of the two attributes matched. Here, on a left outer join, what you're going to get is all the rows from T1 and only the matching rows from T2. and vice versa on a right outer join, right? Get all the rows from the right and only the matching rows from the left, T1 in this case. This one I can see being useful, even though I don't ever remember using it. Where you find all the rows in both tables. And, so what this really means is your results set has a bunch of nulls in it, right? So you have a results set where some of the rows from T1 have nulls for T2, those ones that don't match, and then there's a whole bunch of rows, hopefully. Most rows match T1 and T2 on C1. And then there'll be some other rows that don't match from T2 that have nulls for the T1 variables. Right, so here's an outer join where we say select the P code, the vendor code. Yeah, see, interesting here, we don't specify the table. Right, it must be, you don't need to, because that attribute is unique across tables, whereas the V code isn't. The V code has a key name and a foreign key name because they don't use a naming convention, and so they have to specify that the V code comes from the vendor table. See, vendor name and P code, they are unique across product and vendor, so you don't have to specify them in more detail. Most of our code, since we had unique attributes, you could tell the name of the table by looking at the attribute. What we had was attribute type abbreviation, sort of like a C underscore for a code or a D underscore for a date was a prefix. And then we had some descriptive term, like, so it would be like C underscore customer underscore, I think it was CU for the customer table. So we had like 2-digit abbreviations that were the suffix for every attribute. And that worked pretty good. All your attributes are always unique across all the tables, and you could still see that C underscore customer underscore CU in the customers table, and the C underscore customer underscore BI in the billing table, right? You could still tell they were key, foreign key. So I thought it worked pretty good. Well, so here we have an example of an outer joins, and then the first statement. What you have here is you're going to get the P code, the vendor code, and the vendor name from the vendor left join product on vendor code, vendor.vcode equals product.vcode, right? Primary key of vendor, foreign key, primary key vendor code of vendor equals foreign key vendor code in product, right? V code. So this is going to give you all the vendors, whether they have any products or not. Now the right outer join here is going to give you all of the rows from the table on the right and only the matching rows from the table on the left, vendor. Right? So right join means all the rows from the table on the right, regardless of whether they have a match in vendor, and so that would be all the products, whether they have a matching vendor or not, and only the vendors that match. Well, in the previous statement where we got to see the list of, we also got the vendors that didn't have products. Are you a little suspicious of why we would want this statement? I guess we could use it as sort of a validation or check, but we should never have a product that doesn't have a vendor, should we? Isn't that a business rule, part of our domain that says every product is made by a vendor or is supplied by a vendor? That's so. I guess we're hoping that when we run this outer join, we're going to get 0 rows returned. Well, and the full outer join would give us both any missing vendors, and then the matches, and then any missing products. Well, so crossing a couple of tables doesn't make any sense, right? I mean, here is why would you cross invoice with line? It doesn't make sense for every instance of invoice to occur with every instance of line. That's illogical. Some invoices are for some customers, other invoices are for other customers. Anyhow, don't get me going. And of course, if you don't do anything, if you don't have any where clause, you get sort of that same kind of condition. Natural join, yeah, that's cute, but it should never happen. I guess that's just one man's opinion. You could go to a place where they use stuff like this. And then, you see why this is bad? This is bad because you look at the statement and you have to know other information to know which keys and foreign keys are being used. That's just bad, right? I mean, don't do it. Well, subqueries are really an interesting dimension of SQL. And so what it means is we can have a set a condition in our where clause. This is like one of the easier examples of it. We can set a condition in our where clause where such that we look to see if a certain value is in a list of values, right? And I guess you say, oh, I could do that with my in statement, right? Which we saw in chapter 7, because you could just do in and then have your list, right? Inside parentheses, you have your list of things that you're looking to see if this thing is in. Well, imagine it instead of inside that in statement, you put in another query, right? You put a select statement, and that select statement selects a set of values for that other attribute that you were looking to see if it was in. Follow me? Instead of having an in list that is option 1, comma, option 2, comma, option 3, comma, now your in list is the result of another query. And that would be, if we had that situation, that would be a subquery. And we'll see some here in a minute. And so a subquery can turn one value. It can return a list of values. It can return a whole result set, like a virtual table. And it also could come back with no value. And you're going to design your subquery to fit your condition. Usually there's in the where clause subqueries, that was the one I just described before. What we have is a query that's embedded in a condition within the where clause, and often you can either contain for a single value, And then we'll all look at another one where there's a list of values. So here what we're going to do, we have this question. List all the vendors that provide products. So we select the V code, the V name from the vendor, where the V code is in a list of V codes where we say select the V code from product. So this is just going to give us a list of all V codes that are in the product table, the foreign key. This is a list of the foreign keys, and this is the value of the primary key. Right? So we're saying, show me the information, the code and the name for all the vendors that have products. I guess that's what that said. List of products where the price is greater than the average product. All right, so we say select the P code and price from product where the price is greater than or equal to the result of this query. Select the average price from product. See, that returns just one value. And then we look at every row in product and compare the price of that row to the value of the average price calculated across all rows. And the optimizer is just smart enough to run this query first and get that value, and then run the second query and find the rows from product. Well, we just saw an example of in that previous query. Having subqueries operate on the group by, right? Operate on the results of the group by clause. And we looked at the group by clause in Chapter 7 and talked about how you have to have the same set of variables in your group by. And then the having operates on the results of the group by statement. Right? So we have a where, then we have a group by, then we have a having having clause that further restricts the results of the group by. So list all customers who ordered the product claw hammer. All right, so I'm going for a distinct customer because I really only need to see each one once. Excuse me, the customer code, the customer last name and first name. From customer, join invoice on customer code. Join line using invoice INV number. And this would be interjoin product using P code. Those are all three interjoins. Customer, interjoin invoice, interjoin line, interjoin product. And the way this, works is the optimizer knows what it's going for, and then it goes after it in the way that makes the most sense. In this case, I'm not sure what it would do because this query is a single result. Oh no, it's not. It's a list. It's a list of P codes. So then we say where the P code, the product code, is in this list, and the list comes from the product table. Select the P code from product where the P description equals claw hammer. And so this is going to be a list of P codes, and then our question will be, is the P code for this instance of product in that list? And if it is, give me this information from customer. One thing I see interesting about this attribute list is why aren't there some attributes from like invoice or something? So I guess these are just the customers who ordered the product claw hammer. That's all the information you wanted. Instead of like we got distinct. So if they ordered it twice, we wouldn't know it. Okay, I can live with that. Hey, here's an alternative syntax to this with the same set of join clauses, but just checks where the P description equals claw hammer. I gotta say, I'd be on number 2. I wouldn't do the subquery if I could write this query. You know, one thing about when you have constants like this, you know you have to search every row in product when you are doing that to know if the description equals that string. Right? So you're definitely processing every row in product. Now, here in the subquery, this is going to process every row in product to find the list of claw hammers. And then we're going to have to process every row in product again to know if its P code is in that list. Hey, I think we can say without doubt that the alternative is better, or the alternative is simpler and faster, because the top statement will have to process product twice, and the alternative syntax will only have to process through product once, or through this result set once, and find all the claw hammer descriptions. Oh, that was fun. Whoops. Well, so here's a having subquery. So we say select the P code in the sum of the line units, that's the number ordered from line, grouped by P code, having the sum of line units greater than the subquery select the average line units from line. So what's happening here is there are many rows in line for each P code. Right? If you think across all invoices for all customers, there's many instances or there's likely to be many instances for each product code in line. And so what we want to know is how many have we sold of each product. So we group by that product code and then sum across that group of rows that have the same P code. And once we have that work done, then we apply a having clause, which is something like a where clause, a conditional, right? So that value that we calculate, that sum of units, is greater than the results of this subquery, which is one single value, the average of the line units from line. So show me the products and the number of units sold for all products that sell more than the average number of products. You know, but the thing we're looking at here is this having clause. And what you see is it is a conditional restriction on the results of the group by clause. Well, we also have operators that allow comparisons of values, and also to allow a comparison of any value. And something like this is what it looks like. List all products with a product cost greater than all individual product costs of products provided by vendors in Florida. Boy, that's a detailed question. So, select the P code and the quantity on hand times the price from product where the quantity on hand times price is greater than all of the results of that subquery. And you can see the result of the subquery, the attribute selected, or the single value returned by the subquery is quantity on hand times price. But it's from a set of products that is different. When this part of the clause, right, we're looking across all rows of product. Here we are now selecting from product, right, and we're going to restrict that product where we're calculating this price from, right? So then we're going to say where the V code is in another subquery, which is a list of V codes, because remember that's what in wants. In wants this list of V codes, right, since we have a V code on the left of our in, right? So then we have select the V code from vendor where the state is Florida. So that's going to give us a list of rows of vendors, a list of V codes from vendors who are in Florida. And then this part of the first subquery is going to calculate the price for all of those V codes from Florida. And then that's going to then compare this price to all of those prices and find any that are above it with that condition right there. This is cool. This is a nested subquery, right? We have two subqueries here. This one and then this one. And see, this query operates, compares this price. So what's happening here is we're going to go through all of product and we're going to compare this price. Every row of product is going to be compared to all rows of product restricted by coming from Florida. Restricted by where the vendor comes from Florida. That's a nice example. Well, you can also put a subquery in a from clause, because what is a from clause, right? A from clause is where we put our tables. So as long as we return a table, a result set, or something that looks like a table, call it a temporary table, but we can use it. And so here is a query, right? And you can see that here's our from clause. And so what we're doing is we're sort of creating this temporary table with this subquery, right? But then we're giving it this name, right? We're calling it CP1. So we select invoice.customer code from invoice, natural join line where the P code equals that value. So that's only going to return one row from invoice. So that's going to return a row for every line, every product, every time that product was sold from line. All right, same thing for this subquery. So here you have two subqueries, and then you use the alias to give them a name. And now that you've named them, right, if you think about what they are, they're a result set. They're just a list of columns and rows. So now you can use them just like they were regular tables. Right? So I almost skipped over that part right there. Right? Select from customer, subquery one row into CP1, subquery one row into CP2. So select where the customer code equals CP1 customer code, and CP1 equals CP2 customer code. So that's all people that purchase both of those products. The customer code equals, this is just to get this part of the clause, this clause in this statement, or this expression in this clause, is just about making the join so that you can get the customer last name from customer. And then this join, where CP1 customer code equals CP2 customer code, shows you where or finds the cases where two customers purchased, the same customer purchased those two different products. So you can see that the subquery is a very, very useful idea. Well, you can also have subqueries in the attribute list. And so if we want to take a look at that, so here we have a query, and it's going to try to list the difference between each product's price and the average price. So we select the P code and the price. And then we have a subquery, looks like a nested subquery, where we select the average price from product as average price, and another, and the this seems to me like I must be missing something. From product as average price, select, so P price, select average P price from product as average price. That's one statement right there. So we have the code, the price, and the average price. And then we select the price minus, the same statement, price minus the average price as the difference. Another one, list the product code, total sales by product, contribution by employee of each product sales. All right, so I'm going to select the P code and the sum of the units times the price as sales, and then I'm going to select the count from employee as the number of as E count. And then I'm going to sum the units times the line price divided by the number of rows per employee as contribution. Well, that's interesting. Right? So you have the total, you have the code for the product, the total sales of the product, the number of employees that you have, and then the contribution, which is the sum of your line units, your sales, divided by your number of employees. And then select all that from line and group by product code. I'm just looking at that for a second and wondering what it really... List the product code, total sales by product, and contribution by employee of each product sales. Yeah, essentially you're dividing product sales by the number, each total product sales by the number of employees. I don't know. Well, a correlated subquery is when the outer statement and the inner statement are joined. When you have an attribute from the outer query used somewhere in the subquery. So the idea is that you are working on the rows as you as you go. There's a connection between the row in the outer subquery and the row in the inner subquery. Now, in some of the other ones we've done, that really wasn't true, right? Our subquery was its own standalone thing, like count the number of employees, right? That subquery didn't have any relation necessarily to the outer statement, except that it was going to be used in the calculation. And it wouldn't have had to been, the optimizer would have been smart enough to only calculate it once. Correlated subqueries, the statement that the subquery is embedded in has attributes that are used within the subquery. All right, so list all product sales for which the units sold is greater than the average units sold for that product. So I'm going to select the invoice number, the product code, the line units from the line named LS, where the LS line units is greater than, select the average units from line labeled LA, where the LA product code equals the LS product code. You see how this attribute comes from the query that is, or comes from the part of the query that is outside the subquery. That's what makes it a correlated subquery. That when attributes from the outside statement are used inside the subquery, it is a correlated subquery. Well, so here we have a subquery as an attribute. So we're selecting the invoice number, the product code, the number of line units, where we are selecting the average line units from line at line named LX, where LX product code equals the LS product code. Down here's our from statement, where we say from line renamed or alias LS, right? So the outside or the outer statement, the larger statement in which the subquery is embedded, right? That attribute is coming from a row of line as LS. Right, so you should just imagine LX and LS are duplicate tables of line, right? And this average subquery is working across the rows of line for each P code in the line LS. So what you're doing is you're stepping through LS, and every time you step to a new row of LS, you're running this subquery to calculate that average line units. And then you just keep doing that until you get to the end. And then here we have in the where clause, another subquery where we're calculating the average line units. The average line units were for the also is a correlated subquery. All right, so that gives us the average line units for a line. And so what we're finding is the LS line units that are greater than average. And then we are showing what that average is. So what we're showing here is the invoice number, the product code, and the line units that are higher than the average, and the average units sold. That's a nice example too. Maybe I just like subqueries. Well, so I think subqueries are really really useful and important to understand. I don't know that they're that difficult. I think the thing to remember is you have some conditional statement usually. And what you want to do is make sure that the condition that you want, that the subquery returns the kind of value that that comparison needs. And as long as you think like that, I think you'll be okay. Well, a lot of the power of SQL comes from functions that are primarily used in the select clause, on the where we are working on attributes, where we might have a date and we want to convert it to a character, or we have numbers that we want to convert between different data types. So there's a lot of functions that are built into SQL for these purposes, and you can use them anywhere, but we mostly use them in the attributes in the select clause. And we've already seen some numerical calculations and things, but you can imagine you'd want to calculate the square root. You'd want to have many different types of functions that you would need, or that similar to what you do in other programming languages when you have to convert a string, and we often have this need for these kind of things whenever we are bringing data in from the web, which is always coming in as text, right? So we have to convert it somehow to a form that is consistent with the data type in the database. Well, databases have a lot of date and time functions. I guess we shouldn't be surprised by that, but it is definitely true that we are always manipulating dates. And dates are stored in what's called a Julian format, right? And Julian format is from one point back in time, such that we are able to record all of, or most of, actual human history. And so you have to convert your dates back and forth in most systems. So they'll take that date format that you give it, and usually you give it a format string too, and then convert that into the way it stores dates in the system. And other things like calculating dates, how much time between dates, we have functions for that. And but dates are really important, much more important than I realized when I first started. So here's a couple little examples of date functions, right? And I guess they're pretty straightforward. Here we have the function toDate, and what we're doing is we're taking this string, because at this point it's not a date yet, it's a string, and then this is a date format, and what we're trying to do is take this string and create a date, and then we're going to do a mathematical operation, and we're going to subtract that date from employee date of birth, divide that by the number of days in a year to come up with a years old kind of measure. So here we have a question everyone is burning to know the answer to. So how long is it till Christmas? Well, if we convert Christmas Day to a date and then subtract from it the current sys date, right? And I guess we would have to put 14 here. We would get a number, and that number would be how many days it is till Christmas. And here's something that we do in Oracle more. Dual is like a fake table, right? And you can use Dual to make calculations and things like that. We'll probably see more of this in our stored procedures as we move forward. But dates are really common thing, and you have to, you have to be able to handle dates, and it takes a little thinking at first, but once you get the hang of it, it's fine. There's all kinds of other functions like sign function and logs. Yeah, there's lots of numeric functions. You want to take the log of something, you want to do a square root or raise it to a square. Um, and so, depending on the problem domain that you're working in, you'll use these or you won't. Now, they're not the same as like the sum and the average and things that work across a lot of rows. What these do is usually take a value and return a value. There's just like a function in a programming language. Well, here's a couple examples. You can get the absolute value. You can do rounding to some level of precision. So we say select round the price to one digit as price one, and to price to zero. Um, Zero decimals as another price. Whoops. Ceiling and floor, you might want to use something like this. I think these things are pretty rare. Here they say Access doesn't even support these functions. Well, string functions are really important. You know you're going to have to manipulate strings. Every programming language has to be able to manipulate strings, and almost all of them just use simple functions. And those same simple functions are implemented in SQL too. Well, conversion. We always have to convert our dates, and that is a new thing that's different from many of our other programming languages, where we don't dates are more for presentation to the user rather than some true data field that we depend on and use. And we often had dates as part of our keys too. So we did a lot of date activity and a lot of conversions. Once you get the hang of it, it's okay. But there's a lot of syntax associated to date conversions, especially when you get down into time dimensions. Well, you remember that we talked before about how the relational model is built on set theory. And so we also have set operators that are implemented and we can use when we're writing SQL statements. So like what we do is we write two statements that are consistent with each other, and then we can union those two statements together. And the kind of thing that I've used this for is to like union all of the items that are on a particular survey to with all the items in that I have data for. And we'll see one of my union queries when we look at our online survey system, the part of it that extracts data for analysis uses a union query. And union compatibility means that the two queries that you're going to try to union the results together from, right? So you have query 1 and query 2, and then you union the results of those two queries. Well, they have to have the exact same number of attributes, and each of the attributes has to be the same data type. If the first attribute in the first query is number 10, then the first attribute in the second query has to be number 10, and then matching as you go on. Well, you can also use, there's a union all query that gets you, retains all your duplicate rows and brings in both the full sets of both tables. Intersect does what you would think it does. It just gives you the ones that appears in both. Minus is the idea that we want to have only the rows in this table that don't appear in this table. And I haven't really seen too many people use intersect or accept in any SQL. There's always some syntax alternative except to union, and I think people go for what they see as simpler. And there's almost always multiple ways to do things in SQL. So here's an example of a union query. It has two select statements. Both of the select statements have customer name, customer last name, customer first name, customer initial, customer area code, and customer phone. Last name, first name, initial, area code, and phone. So we have two tables, customer 1 and customer 2. And this is going to give us a union of the rows in both of those tables with the duplicates eliminated. The union all statement here is going to give us all rows keeping the duplicates. And this idea that they have the same set of attributes and those attributes have the same data types is the union compatibility concept. All right, select the customer code from customer where the area code is 615. That gives us a list of customers from that area. We intersect that with the distinct customer code from invoice, which is all the list of customers that have provided invoices. And so the intersection is going to tell us these are the customer codes these are the customer codes for the customers that have placed invoices and live or have the area code 615. Excuse me. And here we say select code from customer where customer area code equals 615 and the customer code is in, then select distinct customer code from invoice. Boy. Yeah, I don't think there's any difference in efficiencies or anything like that there either. My guess is you'd see this one before the other one. I don't know why people wouldn't like set theory, but I can see where they might not do the above statement. and just go for the simple syntax from below. Well, you remember our minus from our set theory. Here's the similar idea where, like our intersect query, we first select for all the list of people with area code 615, and then we see if any of those customers in our database have not given us any invoices, right? This is the list. The first half of the query gives us the list of all the people with that area code, and the second half of the query gives us all the people that have given an invoice. So if there's any rows returned by this entire query, right, these queries return a set of rows that go across both of the pieces of the query, and that's why the semicolon is at the end of both of them. This would tell us if we have any people that are from that area that have never placed an invoice. Whoops. Again, I'd stick with the alternate syntax for this one too, probably. Well, views are really useful. We did a lot of views for users to query from. And we're going to learn something later in our lecture here about dynamic SQL. And so what we did is we created views that did all of like the interesting joins. And then we created we wrote like a program that created dynamic SQL based on user choices off of those views. And then so generated the SQL and then executed it in sort of in a runtime way. But that's where we made a big use of our views. From a programming perspective, I think we didn't use a lot of views. We went directly to our tables. And you can see if you do views and everybody works through the views, you could then maybe have a little more flexibility by changing the view and not have to change any of the programs, where if you change the tables, you might. Well, so the view is just a query. Right here we say create view product _to order as the results of this query, which is select the product code, the description, quantity on hand, and price from product where the quantity on hand is less than the minimum order number plus 10 items. And then once you create this view, anytime you want to see, well, what is on the list of products to order, you just say select star from products to order, and you use the view name as the table name. And you'll see in my online survey system where we have some embedded SQL, I do something like this, where I have queries saved in the system, and then I call those queries from my program code that displays the survey. Well, so here's another view where we are, for each vendor, we're coming up with the sum of the quantity on hand times the price. What is the maximum quantity on hand we've had? What was the minimum quantity on hand we have? And what is the average quantity we have on hand from product, but for each vendor, grouped by vendor code. Right? So we get a V code, and then a total cost, max quantity, min quantity, and average quantity. And if this view is used a lot, the system may calculate it in advance. Although with these sum values in there, anytime product change, you'd have to come back. Or with these aggregate functions, every time product change, you'd have to come back and recalculate it. But whenever you want to use this, you just say select star from product stats. And so what what you're saving is people don't have to really know how those things were calculated. Maybe it could be a more complex calculation or where clause or something like that that you don't really want people to see if they're not capable of really understanding it. Because people will want to understand, and they will then ask a whole bunch of questions that aren't really worth answering, or they aren't important questions. Well, an updatable view is one that is going to be row specific, such that it's going to match a row by row to the tables that are part of it. We don't usually do update through views. We always update it directly to our tables. But there are some restrictions that if you do update through views, you're limited. And those limits pretty well. If you can't do joins and things, you're pretty well out of the ability to do something useful. Well, in Access we have the auto number idea. Every time a row is inserted into the table that has an auto number field, that number gets incremented, and then we use it sometimes for like a primary key. Order number, invoice number is like the perfect example. So Oracle doesn't have that feature. What it has is a way to generate a number, and then you use that number that you generate as a value in your insert statement, or whenever you create a new row in a table. And so it's called a sequence. And the syntax looks like this: is you say create a sequence and give it the name. Here's the customer code sequence. And then it's going to start with a number. The first customer will be 20,010, and the next one will be 20,011. And then when you go to insert you want to use this sequence, code sequence that you created. When you go to insert a new instance or a new row into customer, you use the sequence and give the next val method. And so that finds what the current val is, and then updates, that adds one to it, writes it back to the sequence so that the next person that uses the sequence gets the next value, and then inserts this value returned by this statement code sequence dot next file as the probably the key in this instance of customer. It's a simple idea, but it's just different than what you're used to in Access and other systems that have an auto number feature. Well, the procedure SQL is really important because, it's one thing to learn all these SQL statements and what is a from clause and a where clause and all that, but really what you're going to be doing is you're going to be putting these statements into programs. And so that's what procedural SQL is about. It's about ways to write programs, and what we use procedures in some instances, and anytime you have a trigger, you have to use a procedure. And so what it is a set of SQL statements that are going to be executed as a block. And then you can have things like procedural kinds of programming embedded in these blocks. So we can have loops, we can have if statements, we can have any number of things that are very common to programming. So there's a number of languages. Oracle's is PLSQL, and it is definitely a way of allowing you to execute programs in the way that you're used to, or in a similar way that you're used to, using SQL. And so what we will do is we'll create this procedure, and then we'll save it in the database. And then instead of writing SQL in our program, we will call the procedure and pass in a set of parameters. And then the procedure will accept those parameters and execute an insert statement for us. And that's just sort of like a simple example. So data types are similar. We have only dates, numbers, and characters. And so if you think about this, you have these data types coming in from a web form or who knows where. And then what we're going to have to do is make sure that the data type of the thing we have matches the data type of the column in the database that we're going to try to put it in. Well, so here's a couple simple examples. So this is what's known as anonymous block because it doesn't have a name. Right, so we say we're going to display server to the output. Here is our begin. Every procedure has a begin and end, and then we only have one statement in here. Insert into vendor these values: 25772, clue store, IZKs, 456, Virginia. Who knows what that last attribute is? Right, and so now we have a new, and then we give an output line, new vendor added. Now I'm not saying these are ones you would find, but it's just giving you the idea of the syntax. Right, now here's another one. We say, we declare our variables with a type. We give them a value. Now we come down and we have our begin and end statement for the procedure. Here we have a while loop. And what we're doing is while P2 is less than 300, we're going to select the count of the P code into the WNUM, right? Here's WNUM, right, which is one of our variables, from product, where the price is between P1 and P2, WP2, so between 0 and 10. And then we're going to output the line, there are X number of products, or WNUM products, between price 1 and price 2. This should be WP1 equals WP2 plus 1. P2 equals P2 plus 50. That's an interesting query as you think how it's going to go through there. It's going to go through there every time, and it's going to count P codes, and then it's going to increase its price, but it's only going to go through there 6 times, right? Because P2 is 300. Usually in these loops, you wouldn't see a condition like this. You'd see an end of file condition. Right, and I think we have one down here. Well, this is the more normal kind of procedure you would have. See, it starts with create a replace procedure, procedure cursor example, PRC underscore cursor underscore example is the name of this cursor. And so here we have a variable, WP code, and it's the same data type as the P code in the product table. We have a description, same type as the description and data type in the product table. We have a total, which is the number 3. we have a cursor, and a cursor is what we use to manage a results set inside of a program. So what we do is we execute a select statement to bring all of the rows from the database into our cursor, and then we process that cursor row by row usually. Okay, so here what I'm doing, my cursor is PROD_cursor, and I'm selecting the product code in the description from product where the quantity on hand is greater than the average quantity on hand from product. Right? That's my cursor. Right? And so here's my begin and end statement for my procedure. Right? So let's see. I'm doing an output line to say I'm going to have products with the quantity on hand greater than the average quantity on hand. Right? Next thing is I open my cursor and I loop. I fetch a row fetch a row from the cursor into my variables WP code and WP description that I declared at the top of the procedure. And then, so I get those values into those variables. Then I have my exit condition. If I have just did a fetch and had a not found, then I'm going to exit my loop. Otherwise, I'm going to print my message saying the code and description I found, and then I'm going to loop. When I'm all done, I'm going to say how many I processed. Oh, and look, I'm using the row count from my cursor. And then I am done, and I close my cursor. And that's the way programs work. And embedded SQL, which is when you put the code right in your program, works in a similar way too. Here what you have is this is a procedure that would then be stored in the database, and whatever it was called would do this task. Well, a trigger is a procedure that is executed when some condition happens. So let's see. Suppose what you have is before you insert a line of invoice, what you want to do is check to see, or check to be sure that there's a customer for that invoice. And you can do that with a trigger. So there is some triggering action, which is always some sort of insert, update, or delete some activity on a table. And then when that activity happens, when that event occurs, this trigger procedure is executed. All right, let's take a look. And here we have our trigger. We say create or replace trigger, trigline _prod, right? After insert on line. So anytime a row is inserted into line, what we want to do is for each row, we want to update product and set the quantity on hand for the product minus the number of units that were just purchased. And new is a special attribute, right, that refers to the line units of the row about to be inserted, right? So we have the insert row, and this is how we reference attributes that are in the row that we are about to insert. And that makes perfect sense of what we would want to do is, if what we're going to do is sell a product, then we want to reduce the quantity on hand, and we could do that with a trigger online, because a new row in line means that there is a sale. Here's another trigger example. So we're going to create or replace the trigger trig line cus. After an insert on line, for each row, we will have a customer variable and a total number variable set equals 0. Begin. This trigger fires up after an insert of a line. It will update the customer balance in customer. Oh, that's a good idea. First thing we have to do is get the customer code. So we select the code, customer code, into WCUST from the invoice, where the invoice number equals the new invoice number from the new row of the line table. Now that we have that new, we got the new invoice number. We have calculate the total for this new line, which is the new price times the new number of units. And then we update the customer balance. We set the customer balance equals the customer balance plus the new total for this invoice, where the customer code equals the customer code that we selected into WCUST right there from invoice. We're using the new invoice number. I think it's good for you to, just think about an area somewhere out in memory named new, where all the attributes from this line that has just been inserted are available for you to process. And I think this is another one of those things, once you do a couple, they become pretty simple. Well, I've been talking about these procedures as though we've already been storing them, but the truth is we didn't talk too much about that yet, right? But that's what we would do. We'd store them. And you can see the advantage of, if you have a statement that's going to be executed by many different programs, having it as a stored procedure makes a lot of sense, because then each programmer won't have to put the actual code in their program. They'll just have to put in a call to that procedure with the appropriate set of parameters, so that if for some reason you have to change that procedure, then you won't have to go back and change it in every program like you would if the actual SQL was there instead of in one place, called by many places, and stored right in the DBMS. Well, cursors are really important. The idea is that you bring the result set from the DBMS into your program using a cursor, and then you can process through that cursor with a loop, and one row at a time, and do whatever you need to do. And we'll see a cursor. It'll be embedded SQL cursor, but we'll see this idea in the online survey system when we talk about web-based databases. Well, the open, fetch, and close of cursors is just used to make things easier. It's a way to go to the next row, and then we also have the idea of, we're going to keep processing. We're going to open, then we're going to fetch until we reach the end of file, and then we're going to close. There's a couple variables associated with our cursor that we can that we can know. Row count tells us how many things were fetched. Not found means that we've reached the end of file usually, and it's often our exit condition. Well, so here's a procedure example that looks kind of similar to the last one we have, but it is a cursor, where first thing you do is you declare your cursor here, right? This is a select statement that's going to return a set of rows, and those rows are going to be our cursor. Then we have this statement which actually executes the select, right? It opens the cursor, meaning that it goes to sends the select statement to the DBMS. The DBMS then parses it and figures out the result set and sends that result set back to our cursor, making it available in this way through our program. And then we loop through it and fetch the next row in the cursor and then process it. In this case, our processing is only to display it, but that's what the fetch does. It brings our values from the result set from the DBMS into our variables inside of our program, and then in this case, we just print them out. And then the exit of our exit condition for our loop is this idea of when the cursor is not found. When that becomes true, that means we've reached the end of file and processed all of the rows, and we should exit our loop. Well, a function is like a procedure except it only returns a value. And they are sort of designed just to be functions to use within PLSQL, similar to the way you use functions in other programming languages. And so it has those capabilities. It gives you that capability to write not only to write a function, something like a subroutine. Well, embedded SQL is when you take your SQL statements and put them right into the host programming languages. Like we're using VB in an ASP active server page Visual Basic is what I have my code written in. And so, but you can embed SQL in any language. There's ways to execute it. And so what you do is you develop and test your SQL in the system in sort of an interactive way, and then you put it in your program, and then you can execute that SQL statement from your program. And when it does execute, what happens is you get a result set, and that result set is in a cursor, and then you can then step through that cursor in your program in the same way as you can step through it in a stored procedure. You can step through it in your program, which could be C or C++ or Java, or in my case, I use VB as our scripting language. Well, it's possible to get some data type mismatches and things, but this is all worked out in development time, so it's never a big issue. It's important that when you take input from users, that you process that input sufficiently that it will these kind of things will never occur. You won't have any data type mismatches. And there are new techniques for doing more set updates and things like that, but I'm still thinking embedded SQL is probably the highest amount of of existing SQL programs, or SQL that is in programs, which is almost all SQL. As I said, there's not a lot of SQL that's done interactively. So I would say most of the SQL that's out there is embedded at this point. Although people are moving more and more to stored procedures. Well, the syntax is very simple. It is straightforward. You have the same ideas of you have to create a connection, you have to open a connection, then you have to execute SQL statements against that connection, and that's basically how it works. And but so it gives you the ability to bring uh, variables from the DBMS into your program and to write values from your program variables into the DBMS. Well, we never really know um, what's going to happen when we execute an SQL statement. Perhaps the parser's down, perhaps there's some problem somewhere else in the system. So we have these variables that we can use to test in our program to see if the SQL that we've executed works. And we can use these both in procedures and in embedded SQL situations. Well, we do mostly static SQL. And that means we just write the SQL statements and put them into our program and then execute them in the program instead of executing them um, interactively in the environment. And they're never going to change once they go in the program. Never may have been a stretch. They're unlikely to change once they've been in the program. They're only going to change if new features are needed and the program is changed in some way. This is the kind of embedded SQL that we have in our online survey system that we'll talk about later in our lectures on web-based systems, which I like talking about that system because it's interesting and it's a little bit detailed. It gets you, I'm sure, outside of the comfort zone of most of your programming experiences, meaning that it's a little bit more than you would have done before. Now, in industry, I done some dynamic SQL, and that's where what you do is you build your SQL statement dependent on choices made by the user, and so we used it to sort of give the illusion of being able to write your own queries, right? Users would go through and select tables and attributes and things, and then we would generate an SQL statement based on what they did and what we knew about our key foreign key structure, and then give them a set of data that met their criteria and using the variables and things that they wanted. And it's an interesting approach, but it's sort of you use it when you don't really know what SQL statements you're going to have to run. And that it's unusual in most programs that aren't associated with some sort of ad hoc query that you would need it or use something like it. Well, I think by now you're looking at this and saying, yeah, boy, SQL does have a lot of power. Yet it is still relatively succinct and I think easy to learn. And it's I guess it's easy, especially when you compare it to other kinds of programming languages that you that you use. Well, inner joins, outer joins, join is what makes the relational database world go round. Hopefully, as you come through these last two lectures on SQL, you're seeing how cool you are by learning to do your key foreign key structure and giving you the ability to really combine your tables in very unique ways. And subqueries are a very powerful, useful tool. we saw places where we had nested subqueries, where a subquery had another subquery nested within it. Well, finally, the procedural SQL, really important. Triggers are really valuable for maintaining the integrity of our database, like where we saw to update a customer balance or to change the quantity on hand. Stored procedures are becoming more and more common. Sometimes they can already be pre-compiled and optimized by the DBMS, so they could be even more efficient than embedded SQL statements where the actual SQL is just embedded directly into the program. Well, I hope you're enjoying these lectures. I think this is a good strategy still, and I think it makes our class more interesting in the live session because we can take more questions, and I think there's plenty of information in these recorded lectures, and I think the last two on SQL, there's a lot of information there, but I think we've done a really good job of covering what you need to know. And so the next thing we need to do is get you to execute enough SQL statements or to write enough SQL statements that you start to feel pretty comfortable with it.